Anyway, I hope it's recording right now. If it's not, then this is going to be a beautiful problem going to waste. All right, so we throw a rock in a pond, and what happens is that radius is going to spread, and let's just say that radius is going to grow at 6 inches per second, okay? So, now, if you think about what's happening here, that radial distance is growing. It's going to grow at a constant length. But while it's growing at a constant length, the area of the ripple is not growing at a constant length. Because the bigger the circle gets, like 6 inches right here does not grow, as far as area is concerned, as much as 6 inches does out here, because you got 6 inches all around. So from 6 inches to 12 inches, this is a lot greater area than just this little portion in here. So, and likewise, the further out we go, the faster the area is going to change. So we're going to throw a rock in a pond, and its ripple is going to grow at 6 inches per second. At what rate is the area changing when the ripple is, let's say, 8 inches out? Okay? Well, area is equal to power squared. So from that, area being power squared, we're talking about changes. We're talking about changes in area, change in radius. So if we're talking about change, guess what we need to do here? What? Find the derivative of this, yes. Now, there's one common link that's happening here. Everything's happening with respect to time. The ripple's area is changing with respect to time. The radius's length is changing with respect to time. So everything's going to have this common value of time. Just like when we do slope, we say our change is with respect to x, because that's how we measure slope. It's rise over run, so everything's with respect to a change in x. Well, here, our change in area is going to be with respect to time. So we're going to treat this a lot like what we did when we did implicit differentiation problems. All right, well now what's going to be the derivative of power squared? Well, it's going to be 2 pi r, but again, r is not, so it's going to be dr dt. Is there a question about what I did there? So I'm taking the derivative just like I normally would. All right, well, the rate of change of the area is what we're wanting to know. So we have 2 pi times, all right, now what is the radius length that I'm interested in? 8. And my rate of change of my radius is what? 6 inches per second. Now, you're not going to have to write down the units. In fact, I'm going to encourage you not to write down the units, but I just want you to see what happens with the units here. So we have 2 and 6 is 12, 12 and 8 is 96. So we get 96 pi. Inches times inches is, yeah, square inches per second, right? And that's going to be dA dt. Now think about how do we measure area? How do we measure area? In terms of square units, right? So if we're talking about at what rate is the area changing, it should be in terms of square inches per amount of time. Does that make sense? All right. So at the instant that the radius is 8 inches, the area is changing at 96 pi square inches per second. All right, well, let's go to a similar type question. Let's think about blowing up a balloon, a spherical balloon. We're going to blow up a spherical balloon. Okay, that's just the mouthpiece right there. And as we blow up the spherical balloon, we're going to blow it up. Let's just say we're going to blow in it at one, no, one's not fun. Let's say 3/2 cubic inches per second. Now, have you ever noticed that when you blow up a balloon, you'll start blowing it up and you see, like the first couple of blows, you see it changes a lot. But then as you blow up the balloon even further and even further, you don't recognize quite as much a change in the size of it, although it is. It's still changing at the same rate as far as volume is concerned, but the further out the balloon gets, when you're blowing it up, the less you see that, because it takes just, if the volume's changing at a consistent rate, then your amount of volume is just barely pushing it out. As far as, I'm sorry, let me back up. The amount of change you see in the radius is barely changing at all. So we're back to here. We got 3/2 cubic inches per second being our volume. Now, volume of a sphere is 4/3 pi r cubed. Volume of a sphere is 4/3 pi r cubed. So again, this time we want to take the derivative. So we get that dv dt is equal to 4 pi r squared, and then this would be dr dt. So we want to know at what rate is the radius changing. And let's just say when the radius is, I don't know, 5 inches. So at what rate is the radius changing when the radius is at 5 inches? Well, dv dt is 3/2 cubic inches per second. So it's going to equal to what here? No, we've already done the derivative, sorry. So it's 4 times pi times 25 times dr dt. So we get 3/2 over 100 pi equals dr dt. Someone do that as a decimal. It'd be the same thing as 3/200 pi. And again, it's going to be, remember this is square inches and this is cubic inches. So cubic inches divided by square inches would be just linear inches. So it's going to be inches per second. But we got 3 divided by, and make sure you put 200 pi in parentheses when you do that division. Point 0.0048 inches per second. So you don't see very much of a change in the radius when the radius is out to 5 inches.
Where did we get the 25 from?
We were interested in when the radius was 5.
And then where did we get the 8 from in the other one?
We were interested in when the radius was 8. It's just part of the problem.